In the quiet darkness of the universe, where stars drift like forgotten dreams, 1,000 mysteries whisper across the void. Tonight, we wander into that silence. There are puzzles in the cosmos that even our brightest minds can't solve, questions older than time, phenomena stranger than imagination, and secrets hidden in the cold light of distant galaxies. From dark matter and unseen stars, to impossible planets and echoes from the beginning of everything, the universe is full of wonders we cannot explain yet. So lie back, breathe slowly. Let your thoughts drift with the stars. Tonight, you will fall asleep to science as we explore 50 cosmic mysteries that remind us how little we know and how beautiful the unknown can be. Close your eyes and let the universe hold you. The journey begins now. On August 15th, 1977, something extraordinary happened at Ohio State University. A radio telescope called Big Ear was quietly listening to the cosmos, as it did every night. But on this particular night, it heard something that still sends chills down the spines of scientists nearly 50 years later. For 72 seconds, the telescope detected a radio signal so powerful, so precise, and so unusual that astronomer Jerry Eamon circled it on the computer printout and marked it with astonishment. The signal came from the direction of the constellation Sagittarius, near a group of stars about 120 light-years away. What made it remarkable was its frequency. It broadcast at 1420 megahertz, which is the exact frequency that hydrogen, the most common element in the universe, naturally emits energy. Here's why that matters. Scientists believe that if intelligent life wanted to send a signal across space, they would use this frequency. It's like a universal channel that anyone studying the cosmos would be listening to. It's the cosmic equivalent of leaving your porch light on. But here's the mystery. We've never heard it again. Despite decades of searching with more powerful telescopes, despite listening to that same patch of sky hundreds of times, the signal never repeated. It appeared once, spoke for just over a minute, and then vanished into silence. Was it aliens trying to contact us? Was it a natural phenomenon we don't understand? Was it interference from a passing satellite or airplane? Scientists have tried every explanation, but none fit perfectly. The signal was too strong and too focused to be random noise. It was too brief and too isolated to be a satellite. And it came from a point in space far beyond our solar system. The WOW signal remains one of the most tantalizing mysteries in the search for extraterrestrial intelligence. Somewhere in the universe, something transmitted a powerful message, and we may have missed our only chance to hear it. Now imagine looking at a map of the entire universe when it was just 380,000 years old. Scientists can actually do this by studying something called the cosmic microwave background, the faint afterglow of the Big Bang that fills all of space. This map should be mostly uniform, with small variations in temperature scattered randomly across the sky. And it is, except for one region. A region so strange that it's been called the cold spot. The cold spot is enormous. It stretches across about 1 billion light-years of space. If you were standing in the middle of it, you'd be surrounded by a void so vast that it contains 10,000 fewer galaxies than it should. But here's what makes it truly mysterious. The cold spot appears colder than its surroundings in the cosmic microwave background. It's about 70 millionths of a degree colder than the average temperature of space. That might not sound like much, but at cosmic scales, it's huge. Statistically speaking, something like this should only occur once in every 50,000 universes by pure chance. Scientists have proposed many explanations. Some suggest it's a massive supervoid, an enormous empty region of space where fewer galaxies formed. As light travels through this void, it loses energy, making the background radiation appear cooler. But even the largest known voids can't fully account for how cold this spot is. Others have suggested more exotic possibilities. Could it be evidence of another universe that collided with ours in the distant past? A cosmic bruise left over from a collision between bubble universes? Could it be a tunnel or bridge to another dimension? Some researchers have even wondered if it might be an error in our understanding of the universe itself. A place where the laws of physics work slightly differently. A hole in the fabric of space-time. The truth is, we don't know. The cold spot sits there in our sky, in the constellation Eridanus, a massive unexplained anomaly in an otherwise uniform universe. It's a cold, dark mystery that challenges everything we think we know about how the cosmos formed. Deep in space, something is screaming at us. These screams last just a few milliseconds, shorter than the blink of an eye, but they release as much energy as the sun produces in an entire day. They're called fast radio bursts, and they're one of the most perplexing discoveries in modern astronomy. The first one was discovered in 2007, hidden in old data from 2001. An astronomer named Duncan Lorimer found it while reviewing records from the Parkes radio telescope in Australia. It was so bizarre that scientists initially thought it must be interference from a microwave oven in the observatory kitchen. But it wasn't. It came from a galaxy billions of light years away. Since then, we've detected hundreds of these bursts. They come from all directions in space, appearing randomly and without warning. Most happen just once and never repeat. But some repeat in patterns that make no sense. There's one called FRB1 80916, discovered in 2018, that repeats on a 16-day cycle. For 4 days, it sends out bursts, then it goes silent for 12 days, then it starts again. Why? No one knows. Another one, called FRB121102, has sent out thousands of bursts from the same location. It's like someone out there is desperately trying to get our attention, sending message after message into the void. What could create such powerful bursts of energy? Scientists have proposed dozens of theories. Some think they come from magnetas, which are neutron stars with magnetic fields billions of times stronger than anything on Earth. When these magnetic fields crack or shift, they might release tremendous bursts of radio waves. Others suggest they could come from colliding neutron stars, or black holes consuming massive amounts of matter, or even alien technology. Yes, some serious scientists have considered whether these could be signals from advanced civilizations. Perhaps they're the radio equivalent of powerful lasers being used to propel alien spacecraft across the cosmos. But here's what makes them truly mysterious. The bursts are affected by something called dispersion. As radio waves travel through space, they interact with free electrons, tiny particles scattered between the stars. This interaction causes different frequencies to arrive at slightly different times. By measuring this dispersion, we can tell how far the signal has traveled, and what we've found is shocking. These bursts are coming from distances so vast that the universe was half its current age when they were emitted. The energy required to create a signal that can travel billions of light years and still be detected is almost incomprehensible. Something out there in the deep darkness of space is creating the most powerful radio signals in the universe, and we have no idea what it is. Here's a simple question that leads to a deeply unsettling mystery. If the universe is so vast and so old, filled with billions of galaxies and trillions of planets, where is everyone? This question is called the Fermi paradox, named after physicist Enrico Fermi, who asked it during a casual lunch conversation in 1950. It seems like a simple puzzle, but the more you think about it, the stranger it becomes. Let's consider the facts. Our galaxy alone contains over 200 billion stars. Many of these stars have planets. Recent discoveries suggest that nearly every star has at least one planet, and many of these planets are in the habitable zone, the region where liquid water could exist. Our sun is relatively young compared to the galaxy. There are stars out there that are billions of years older. If life developed on planets around those stars, those civilizations could be billions of years more advanced than us. Now think about human progress. Just 10,000 years ago, we were hunter-gatherers. Today, we're sending robots to Mars and detecting planets around distant stars. In another 1,000 years, who knows what we'll be capable of? In 1,000,000 years, in 1,000,000,000, an advanced civilization with even a tiny fraction of a 1,000,000,000-year head start could have colonized the entire galaxy by now. Even traveling slowly, much slower than light speed, it would only take about 10 million years for a civilization to spread across all the stars in the Milky Way. That sounds like a long time, but it's nothing compared to the age of our galaxy. So where are they? Why haven't we seen any signs of these civilizations? No massive structures surrounding stars to harvest their energy. No radio signals filling the airwaves. No probes visiting our solar system. Just silence. Scientists have proposed hundreds of solutions to this paradox. Maybe intelligent life is incredibly rare. Maybe civilizations destroy themselves before they can spread across the stars. Maybe they're out there but hiding, observing us without making contact. Maybe we're looking for the wrong signs, like ancient humans trying to detect cell phone signals with their ears. Or maybe, and this is the unsettling possibility, maybe there's something ahead of us. Something that happens to every civilization that reaches a certain point. A great filter that no species can pass through. Maybe we haven't seen other civilizations because they didn't survive to become spacefaring. And maybe we're approaching that filter ourselves. The silence of the universe is deafening. We call out into the void, listening for any response, and we hear nothing but the whisper of empty space. Are we alone? Are we early? Are we lost? The answer is out there, somewhere among the stars, waiting to be discovered. About 1,400 light-years away, in the constellation Cygnus, there's a star that's doing something stars aren't supposed to do. It's officially called KIC 846252, but everyone knows it as Tabby's star, named after astronomer Tabitha Boyajian, who first brought its bizarre behavior to the world's attention. Stars are supposed to be predictable. They shine steadily, with only minor variations. When a planet passes in front of a star from our point of view, it blocks a tiny amount of light, usually less than 1%. This dimming is regular and consistent. But Tabby's star is nothing like this. It dims erratically and dramatically. Sometimes it dims by 15%, sometimes by 22%. These dips in brightness last for days or weeks, then the star returns to normal. The pattern is completely irregular, with no predictable cycle. In 2011, the star dimmed slightly. In 2013, it dimmed by 15%. In 2017, it dimmed again by varying amounts. And here's the strange part. Over the century that we've been observing it, the star has gradually dimmed by about 20% overall. That's not supposed to happen in just 100 years. When scientists first analysed the data, they were baffled. A planet couldn't cause such dramatic dimming. Even a gas giant the size of Jupiter would only block about 1% of the star's light. To block 22%, you'd need something enormous, something nearly half the diameter of the star itself. Could it be dust? A massive cloud of dust orbiting the star? Possibly, but dust clouds would cause different wavelengths of light to dim at different rates. Observations show that all wavelengths dim equally, suggesting whatever is blocking the light is solid, not dust. Could it be a swarm of comets? Some scientists proposed that maybe we're seeing the aftermath of a planetary collision, with countless fragments orbiting the star in a chaotic pattern. It's possible, but it doesn't explain everything. The dimming patterns are too irregular, too complex. And then there's the explanation that captured the public imagination. Could it be an alien megastructure? Imagine an advanced civilization building massive solar panels around their star to harvest its energy. These structures, sometimes called Dyson swarms, would block starlight as they orbit. If we saw such a structure from far away, edge on, it might look exactly like what we're seeing at Tabby's star. Irregular dimming, dramatic drops in brightness. No natural explanation. Scientists searched for radio signals from the star. They found nothing. They looked for signs of artificial heat signatures. Nothing conclusive. The alien hypothesis remains the most speculative and least likely explanation, but it hasn't been ruled out. More recent observations suggest the dimming might be caused by an irregular dust cloud after all, one with properties we don't fully understand. But even this explanation has problems. The mystery isn't solved. It's just become more complex. Somewhere out there, 1,400 light-years away, a star is dimming and brightening in ways that challenge our understanding. Something enormous is blocking its light. Something we can't quite explain. And until we figure out what it is, Tabby's star will remain one of the most intriguing mysteries in the night sky. Right now, as you listen to these words, you are moving through space at over 600 kilometers per second. That's about 1.3 million miles per hour. You're not just moving because Earth is spinning, or because Earth orbits the Sun, or because the Sun orbits the center of the Milky Way. You're moving because something immense and massive is pulling our entire galaxy, along with thousands of other galaxies, toward it. We call it the Great Attractor. Imagine a region of space so massive, containing so much matter, that its gravitational pull affects galaxies hundreds of millions of light-years away. The Great Attractor is located about 200 million light-years from Earth, in the direction of the constellations Triangulum Austral and Norma. But here's the problem. We can't see it. The Great Attractor lies in a region of space that's hidden behind the disk of our own Milky Way galaxy. All the stars, dust, and gas in our galaxy's plane block our view. We call this region the zone of avoidance. It's like trying to see through a forest while standing among the trees. The trees themselves block your view of what lies beyond. Scientists discovered the Great Attractor by observing the motion of galaxies. When they measured how fast galaxies were moving and in what directions, they found something strange. Galaxies weren't moving randomly. They weren't simply moving away from each other due to the expansion of the universe. They were flowing, like rivers, toward a common point. By mapping these flows, scientists could infer that something massive must exist in that direction. Something with enough gravitational pull to influence the motion of millions of galaxies across hundreds of millions of light years. But the mystery deepens. Later observations revealed something even more startling. The Great Attractor itself is moving. It's being pulled by something even larger and more distant. A massive supercluster of galaxies called Laniakea, a Hawaiian word meaning immense heaven. Laniakea contains about 100,000 galaxies spread across 500 million light years. Our Milky Way is just one tiny galaxy on the outer edge of this vast structure, all of it flowing toward a central point like water spiraling toward a drain. But even Laniakea doesn't explain everything. There are hints of even larger structures, even greater attractors, pulling on Laniakea itself. The universe, it seems, is arranged in a vast cosmic web of matter, with enormous voids between massive concentrations of galaxies. We're only beginning to map this structure, only starting to understand the forces that shape it. Somewhere beyond the zone of avoidance, hidden behind the glare and dust of our own galaxy, lies a massive concentration of matter. It's pulling us toward it at tremendous speed. And despite decades of study, we still don't fully understand what it is, what it contains, or what role it plays in the larger structure of the universe. We're passengers on a galactic ship, sailing through space toward an unseen destination. The Great Attractor beckons, invisible and mysterious, a gravitational lighthouse in the darkness, pulling us ever closer to secrets we cannot yet see. In 2018, astronomers discovered something that shouldn't exist. A galaxy called NGC 1052. Do AOF. 2U can just call it DF to contain almost no dark matter at all. To understand why this is so strange, you need to know about dark matter. For decades, scientists have observed that galaxies rotate too fast. The visible stars, gas, and dust in a galaxy don't have enough gravity to hold the galaxy together at the speeds they're spinning. By all rights, these galaxies should fly apart, scattering their stars into intergalactic space. But they don't. Something invisible is holding them together, something with mass and gravity that we cannot see. We call it dark matter, and it makes up about 85% of all the matter in the universe. Every galaxy we've ever studied has been embedded in a massive halo of dark matter until DF2. DF2 is a fuzzy, diffuse collection of stars about the size of the Milky Way, but containing only about 1% as many stars. When scientists measured how fast its stars were moving, they expected to find the telltale signs of dark matter. But the stars were moving slowly, exactly as fast as they should move, given only the gravity from the visible matter. It was as if dark matter simply wasn't there. This discovery shocked the astronomical community. If dark matter is a fundamental component of the universe, how can a galaxy exist without it? It would be like finding an ocean without water, or a storm without wind. Some scientists argued that DF2 proved dark matter was real. After all, if dark matter was just a mistake in our understanding of gravity, then all galaxies should show the same behavior. The fact that DF2 is different suggests that dark matter is actually a type of matter that can be separated from regular matter under certain conditions. But how? How did DF2 lose its dark matter? Or was it born without it? Some theories suggest that DF2 was created in a collision between larger galaxies, a sort of cosmic offspring that was somehow stripped of its dark matter in the process. Then, in 2020, other scientists reanalyzed the data and claimed that DF2 might not be as special as we thought. They suggested it might be closer to us than originally measured, which would mean it does contain dark matter after all, just less than typical galaxies. But even if DF2 turns out to be less unusual, we've since discovered other galaxies that seem to have very little or no dark matter. These phantom galaxies challenge our understanding of how galaxies form and what role dark matter plays in the universe. The mystery continues. Are these truly galaxies without dark matter? If so, what does that tell us about what dark matter is and how it behaves? Can it be separated from normal matter? Can galaxies exist without it? And if they can, what does that mean for our understanding of the universe? Scientists try to avoid dramatic names, but when they discovered this particular cosmic mystery, they couldn't resist. They called it the axis of evil. Remember the cosmic microwave background we discussed earlier? It's the faint afterglow of the Big Bang, a snapshot of the universe when it was just 380,000 years old. This radiation should be almost uniform, with tiny random fluctuations scattered across the sky. And it is, mostly. But when scientists analyzed the largest scale patterns in this radiation, they found something disturbing. Certain features seemed to be aligned with each other and with the geometry of our solar system. It was as if the universe had drawn a line through space, and this line happened to point directly at Earth. Specifically, the quadrupole and octupole. These are mathematical ways of describing large-scale patterns in the microwave background, seem to line up with the plane of our solar system and the ecliptic, the path the sun appears to trace across our sky. This is deeply unsettling for one simple reason. The cosmic microwave background comes from the edge of the observable universe. It's light that has been traveling for over 13 billion years, from a time when our solar system didn't exist, when the matter that would become our sun and Earth was still scattered across space. There is absolutely no reason, no physical mechanism that could cause patterns from the infant universe to align with the orientation of our tiny solar system formed billions of years later. It's like throwing dice in New York and having them somehow be influenced by how your house is oriented in Tokyo. The two things shouldn't be connected in any way. Some scientists have suggested that this alignment is just a coincidence, a statistical fluke that looks meaningful but isn't. After all, if you look at enough data, you'll eventually find patterns that seem significant but are actually random. Others have proposed more exotic explanations. Maybe the universe isn't infinite. Maybe it has a specific shape or topology that creates these patterns. Maybe the universe wraps around on itself like the surface of a sphere or a torus, a donut shape, and these alignments are hints of that structure. More unsettling theories suggest that maybe our fundamental understanding of the universe is wrong. Maybe the cosmological principle, the idea that the universe looks roughly the same in all directions and from all locations, isn't actually true. Maybe Earth does occupy a special position in the cosmos, not because we're at the center, but because of some property of space itself that we don't understand. Or maybe, and this is the most uncomfortable possibility for scientists, maybe there's something wrong with our data or our analysis. Maybe this alignment is an artifact of how we collect and process the information, not a real feature of the universe. The axis of evil remains unexplained. It sits in our data, this strange alignment between the largest structures in the universe and the smallest details of our cosmic neighborhood. It whispers a question that science cannot yet answer. Why does the universe seem to know we're here? At the heart of nearly every large galaxy, including our own Milky Way, lurks a supermassive black hole. These monsters contain millions or even billions of times the mass of our Sun, compressed into a region smaller than our solar system. We understand, roughly, how these black holes grew so large. They formed early in the universe's history and spent billions of years feeding on gas, dust, and stars, slowly growing heavier and heavier. It's a gradual process that takes immense amounts of time. But then we looked deeper into space, further back in time, and we found something impossible. Supermassive black holes, fully formed, billions of times the mass of the Sun, existing when the universe was less than 1 billion years old. Some are even more massive than the black hole at the center of our galaxy, despite having only a fraction of the time to grow. This is the black hole growth problem, and it breaks our understanding of physics. Here's why. Black holes grow by consuming matter. But there's a limit to how fast they can grow, called the Eddington limit. When a black hole feeds, it heats up the matter falling into it. This hot matter radiates energy and pressure, which actually pushes away more matter trying to fall in. It's like trying to drink from a fire hose. The force of the flow itself prevents you from drinking faster. Because of this limit, even if a black hole fed constantly and efficiently, converting every bit of matter around it into mass, it could only double its size every 50 million years or so. Let's do the math. If you start with a black hole, the mass of a single star, about the size of the smallest black holes we know, and let it feed at the maximum possible rate for 800 million years, it still wouldn't grow large enough to match what we're observing. These early supermassive black holes are too big, too massive, too developed for their age. They're like finding a fully grown oak tree in a garden that was planted yesterday. Scientists have proposed several explanations, but none fully solve the mystery. Maybe these black holes didn't start from collapsed stars. Maybe they formed directly from massive clouds of gas in the early universe, born already weighing millions of solar masses. But we've never observed this process, and we're not sure if it's even possible under the conditions of the early universe. Maybe they grew faster than we thought possible, feeding more efficiently than our models predict. Maybe the matter around them was so dense, so rich, that they could overcome the Eddington limit somehow. After all, if you look at enough data, you'll eventually find patterns that seem significant but are actually random. Others have proposed more exotic explanations. Maybe the universe isn't infinite. Maybe it has a specific shape or topology that creates these patterns. Maybe the universe wraps around on itself like the surface of a sphere or a torus, a donut shape, and these alignments are hints of that structure. More unsettling theories suggest that maybe our fundamental understanding of the universe is wrong. Maybe the cosmological principle, the idea that the universe looks roughly the same in all directions and from all locations, isn't actually true. Maybe Earth does occupy a special position in the cosmos, not because we're at the center, but because of some property of space itself that we don't understand. Or maybe, and this is the most uncomfortable possibility for scientists, Maybe there's something wrong with our data or our analysis. Maybe this alignment is an artifact of how we collect and process the information, not a real feature of the universe. The axis of evil remains unexplained. It sits in our data, this strange alignment between the largest structures in the universe and the smallest details of our cosmic neighborhood. It whispers a question that science cannot yet answer. Why does the universe seem to know we're here? At the heart of nearly every large galaxy, including our own Milky Way, lurks a supermassive black hole. These monsters contain millions or even billions of times the mass of our Sun, compressed into a region smaller than our solar system. We understand, roughly, how these black holes grew so large. They formed early in the universe's history and spent billions of years feeding on gas, dust, and stars, slowly growing heavier and heavier. It's a gradual process that takes immense amounts of time. But then we looked deeper into space, further back in time, and we found something impossible. There's an invisible force tearing the universe apart. Right now, at this very moment, space itself is stretching, expanding, pushing galaxies away from each other at ever-increasing speeds. We call this force dark energy, and it makes up about 68% of everything that exists. Yet we have absolutely no idea what it is. For most of the 20th century, scientists assumed the universe's expansion was slowing down. After all, gravity pulls everything together, so the expansion from the Big Bang should gradually decrease over time, like a ball thrown into the air, eventually falling back down. But in 1998, two teams of astronomers made a discovery that changed everything. They were studying distant supernovas, exploding stars that act like cosmic measuring sticks, when they noticed something impossible. The universe wasn't slowing down, it was speeding up. Imagine throwing a ball into the air and watching it accelerate upward, faster and faster, defying gravity. That's essentially what the universe is doing. Something is pushing against gravity, overwhelming it, driving galaxies apart at an accelerating rate. This something is dark energy, and it's the biggest mystery in all of physics. We don't know what it's made of. We don't know where it comes from. We don't even know if it's truly a form of energy or something else entirely. Some scientists think dark energy might be a property of space itself. Empty space, according to quantum mechanics, isn't truly empty. It's filled with virtual particles that pop in and out of existence constantly. Maybe these quantum fluctuations create a kind of pressure that pushes space apart. But when physicists calculate how strong this effect should be, they get a number that's wrong by a factor of 10 to the power of 120. That's 1 followed by 120 zeros. It's the worst prediction in the history of science. Others suggest dark energy might be a new force of nature, something we've never encountered before. Or maybe it's not constant at all. Maybe it changes over time, growing stronger or weaker as the universe ages. Some theories even propose that dark energy doesn't exist, and what we're seeing is evidence that Einstein's theory of gravity breaks down at cosmic scales. But if that's true, we need an entirely new understanding of how the universe works. What we do know is that dark energy is winning. Billions of years from now, it will push galaxies so far apart that future civilizations will look into the sky and see only darkness. They'll have no evidence that other galaxies exist. the universe will appear empty, isolated, cold. Dark energy is slowly erasing the cosmos, pulling the universe apart one galaxy at a time, and we can't stop it. We can barely even understand it. The mystery deepens when you consider dark matter. Remember, dark matter is the invisible substance that holds galaxies together. It makes up about 27% of the universe. Scientists have spent decades searching for dark matter particles, building massive detectors deep underground to catch even a single interaction. But the detectors remain silent. We know dark matter exists because we can see its gravitational effects, but we can't find the matter itself. And the way dark matter is distributed across the universe is strange. It clumps together in ways our simulations don't quite predict. Computer models show that dark matter should form countless small clumps throughout galaxies, thousands of little halos of dark matter scattered everywhere. But when we look at actual galaxies, we don't see evidence of these small clumps. There are fewer dwarf galaxies than there should be. The distribution of dark matter is smoother, more uniform than our theories predict. Some regions of space have more dark matter than others, but we don't fully understand why. There are massive filaments of dark matter connecting galaxy clusters, creating a cosmic web that spans the entire observable universe. Galaxies form along these filaments like dew drops on a spider's web. But the details of how this web formed, why it has the structure it does, remain mysterious. Dark matter, this invisible scaffolding that holds the universe together, refuses to reveal its secrets. Here's a question that should keep you awake at night, though we hope it doesn't. When the universe began, the Big Bang should have created equal amounts of matter and antimatter. These are like mirror images of each other. For every particle of matter, there should have been a particle of antimatter. And when matter and antimatter meet, they annihilate each other in a flash of pure energy, leaving nothing behind. So why does anything exist at all? Why is the universe made of matter instead of being empty? This is called the matter-antimatter asymmetry problem, and it's one of the deepest mysteries in physics. Somehow, in the first fractions of a second after the Big Bang, something happened that created slightly more matter than antimatter. For every billion antimatter particles, there were 1,000,000,001 matter particles. When all the pairs annihilated each other, that one extra particle of matter in every billion survived. Everything you see, every star, every planet, every atom in your body, comes from that tiny excess. But what caused this imbalance? The laws of physics as we understand them should treat matter and antimatter identically. They should have been created in equal amounts, yet clearly they weren't. Scientists have discovered some processes where matter and antimatter behave slightly differently, phenomena called CP violation. But the effects we've measured are far too small to account for all the matter in the universe. There must be other mechanisms, other asymmetries we haven't discovered yet. Some theories suggest that in the incredibly hot, dense conditions of the early universe, certain heavy particles decayed in ways that produced more matter than antimatter. But we've never observed these particles. They exist only in our equations, hypothetical solutions to an observed problem. Other ideas propose that antimatter didn't disappear at all. Maybe there are entire regions of space, entire galaxies, or even galaxy clusters made of antimatter. They would look identical to normal matter from a distance. But if this were true, we should see evidence at the boundaries where matter and antimatter regions meet, violent annihilations producing characteristic gamma rays. We don't see this evidence. The mystery remains. Somewhere in the physics of the early universe, hidden in the first microseconds after creation, is a process that saved reality itself. A tiny bias in favor of matter over antimatter that allowed the universe to exist. Without it, everything would have annihilated into pure energy, leaving behind an empty cosmos filled only with light. We exist because of an asymmetry we don't understand, survivors of an imbalance we can't explain. Connected to this is another mystery, the lithium problem. When physicists calculate what the Big Bang should have produced, they can predict the amounts of different elements created in those first minutes. Hydrogen, helium, and a tiny bit of lithium. The predictions for hydrogen and helium match observations perfectly. But lithium is wrong. The universe contains only about a third as much lithium as it should. Where did the rest go? Did something destroy it? Did our calculations miss something about how the early universe worked? After decades of research, we still don't know. The missing lithium is a small detail, but it hints that something about our understanding of the Big Bang is incomplete. There are stars in our galaxy traveling at impossible speeds. Astronomers call them hypervelocity stars, and they're moving fast enough to escape the Milky Way entirely, flying out into the emptiness between galaxies. Some are traveling at more than 1,000 kilometers per second, more than 2 million miles per hour. At these speeds, they'll eventually leave our galaxy forever, becoming lonely wanderers in the vast cosmic void. The mystery is how they got moving so fast. Normal stellar processes can't accelerate stars to these speeds. Something violent, something powerful, had to fling them out of their orbits. The leading theory involves the supermassive black hole at the center of our galaxy. If a binary star system, two stars orbiting each other, gets too close to the black hole, the intense gravity can tear the pair apart. One star gets captured by the black hole, while the other gets flung away like a stone from a slingshot, racing away at tremendous speed. But this theory doesn't explain all hypervelocity stars. Some are traveling in directions that don't point back to the galactic center. Some are types of stars that shouldn't exist in binary systems, and the numbers don't quite add up. We're finding more hypervelocity stars than this mechanism should produce. Maybe there are other processes we don't know about. Maybe there are multiple supermassive black holes lurking in the galaxy. Maybe some of these stars came from entirely different galaxies, flung out by catastrophic events billions of years ago. What we do know is that right now, hundreds or perhaps thousands of stars are racing away from the Milky Way at breakneck speeds, carrying their planets with them if they have any. Imagine living on a planet orbiting one of these stars. Over millions of years, you'd watch your home galaxy slowly shrink in the night sky, the stars growing dimmer and fewer, until eventually you'd find yourself in the space between galaxies. Looking up, you'd see only a few nearby galaxies scattered across an otherwise empty black sky. Your sun would be the brightest object in your heavens, a lonely beacon in an ocean of darkness. The hypervelocity stars are cosmic exiles, and we're still trying to understand what banished them. When you look at the night sky, you can see thousands of stars scattered across the darkness. But there's one part of the sky where you can't see much at all. It's called the zone of avoidance, a band stretching across about 20% of the sky, where our view of the distant universe is almost completely blocked. This zone lies along the plane of the Milky Way, where the disk of our galaxy is thickest. All the stars, dust, and gas in our galaxy's disk absorb and scatter light from objects beyond, creating a cosmic blind spot. The zone of avoidance frustrates astronomers because some of the most interesting structures in the nearby universe are hidden behind it. Remember the Great Attractor. It lies in the zone of avoidance, hidden from our optical telescopes. But the zone conceals more than just the Great Attractor. There could be entire galaxy clusters behind it, massive structures that we know nothing about because we can't see through our own galaxy's disk. In recent years, astronomers have started using radio and infrared light to peer through the zone. These wavelengths can penetrate the dust better than visible light, and they've found hidden galaxies, hundreds of them, lurking in the areas we thought were empty. One discovery, made in 2016, revealed a massive concentration of galaxies called the Vela supercluster, containing about 800 trillion times the mass of our Sun. It had been completely hidden from us, sitting in the zone of avoidance, influencing the motion of our galaxy without us knowing it was there. What else is hidden in the zone? How many more galaxies and structures are we missing? The zone of avoidance is a reminder that our view of the universe is limited, that there are vast regions of space we simply cannot see from our vantage point. It's like trying to understand the ocean while standing at the bottom, looking up. You can see the surface, but you miss everything happening above the waterline, between the great walls of galaxies, between the filaments and clusters of the cosmic web. There are voids. Enormous regions of space that contain almost no galaxies at all. These cosmic voids are the largest structures in the universe, some stretching across 300 million light-years or more. If you could somehow be transported to the center of a cosmic void and look around, you'd see almost nothing. A few dim, lonely galaxies scattered across an otherwise empty sky. The nearest galaxy cluster might be over 100 million light-years away in any direction. These voids aren't completely empty. They contain dark matter and dark energy, just much less normal matter than other regions of space. But why are they so empty? How did these vast regions become so devoid of galaxies? The standard explanation is that in the early universe, matter clumped together due to gravity in some regions while other regions remained sparse. Over billions of years, the dense regions grew denser, forming galaxy clusters, while the sparse regions grew emptier as what little matter they had was pulled toward the denser regions. But some voids are so large, so empty, that they challenge our understanding of how structure formed in the universe. The Boet's void, also called the Great Void, is nearly 330 million light-years across and contains only about 60 galaxies. In a normal region of space that size, you'd expect to find about 2,000 galaxies. It's as if someone scooped out a huge chunk of the universe, leaving behind an almost empty bubble in space. Some scientists have speculated about whether these voids could be expanding faster than the rest of the universe, pushed by dark energy in ways we don't understand. Others wonder if the voids might tell us something about the initial conditions of the Big Bang, frozen patterns from the first moments of creation. The cosmic voids are quiet, empty places, vast cathedrals of darkness where almost nothing exists, and yet they make up most of the volume of the universe. We live in the thin, bright regions between these voids, islands of matter in an ocean of emptiness. In the early 2000s, astronomers discovered something strange. When they measured the motion of galaxy clusters over vast distances, hundreds of millions of light years, they found that many clusters were flowing in the same direction, not just falling toward the Great Attractor, but moving with a large-scale flow that extended far beyond what any known structure could explain. They called this phenomenon dark flow. The flow is like a river, carrying galaxy clusters along at about 600 kilometers per second toward a point in the sky near the constellations Centaurus and Vela. What makes this so mysterious is that nothing we can see should cause such a large-scale motion. The structures we know about, even massive ones like Laniakea, can't account for galaxy clusters being pulled in the same direction across such enormous distances. If dark flow is real, something beyond the observable universe must be pulling on these galaxies, something so massive, so distant, that we can't see it because its light hasn't had time to reach us yet. Some scientists proposed that dark flow might be evidence of other universes. In some theories of cosmology, our universe is just one bubble in an infinite sea of universes. If another universe exists beyond our cosmic horizon, its gravity might reach into our space, pulling on the matter near the edge of what we can see. Dark flow would then be the signature of something beyond the edge of reality as we know it, a gravitational whisper from another cosmos. Other researchers remain skeptical. Measuring the motions of such distant galaxy clusters is incredibly difficult, and small errors can create the appearance of flows that don't really exist. Some studies claim to confirm dark flow, others claim to refute it. The debate continues, with observations supporting both sides. If dark flow is real, it suggests that our observable universe is just a small part of something much larger, and that we're being pulled toward regions of space we can never see. If it's not real, it's a reminder of how careful we must be when interpreting data from the very edges of what we can observe. Here's another puzzle that's been troubling cosmologists. When scientists try to measure how fast the universe is expanding, they get different answers depending on how they measure it. This disagreement is called the Hubble tension, and it's becoming increasingly difficult to ignore. One method looks at the cosmic microwave background, the ancient light from the early universe, and uses our understanding of physics to calculate what the expansion rate should be. This method gives an expansion rate of about 67 kilometers per second per megaparsec. That means for every 3.26 million light-years of distance, space expands by 67 kilometers per second. But another method measures the expansion rate directly by observing distant supernovas and certain types of variable stars called Cepheids. These observations give a higher value, about 73 kilometers per second per megaparsec. That's a difference of about 9%, which might not sound like much, but in cosmology, it's huge. Both methods have been refined and checked many times, and the disagreement persists. As measurements become more precise, the tension grows worse, not better. This isn't just a minor calibration error. It suggests that something fundamental might be wrong with our understanding of the universe. Maybe dark energy isn't constant, but has changed over cosmic time. Maybe there's some new physics in the early universe that we don't understand. Maybe our model of how the universe evolved needs major revisions. Or maybe there's some systematic error in one or both measurement methods that we haven't discovered yet, though this seems increasingly unlikely given how carefully these measurements have been made. The Hubble tension is one of those problems that could either be resolved with a simple explanation we're missing, or it could be the first crack in our cosmological model, a sign that we need new physics to explain how the universe works. For now, it remains unresolved, a nagging inconsistency in our otherwise successful theory of the cosmos. Imagine a world without a sun, a planet floating alone in the darkness of space, untethered to any star, wandering through the galaxy in eternal night. These worlds exist. We call them rogue planets, and there might be billions of them in our galaxy alone, possibly even more rogue planets than there are stars. They drift through the cosmos in total darkness, their surfaces frozen and lifeless, carrying with them the faint heat from their formation or from radioactive decay in their cores. How do planets become rogues? Most likely they formed around stars like any other planet, but were thrown out of their solar systems by gravitational interactions. Maybe two planets' orbits brought them too close together, and one got flung away. Maybe a passing star disrupted the system, sending planets flying off into interstellar space. Or maybe they formed in chaotic environments where multiple stars were pulling on them, eventually ejecting them from the system entirely. Some rogue planets might have moons. Imagine being on such a moon, orbiting a planet that orbits nothing, drifting through the void. You'd never see a sunrise. The sky would be permanently black, lit only by distant stars and maybe the faint glow of your planet's heat. No seasons, no years, just endless darkness and cold. Yet even in such hostile environments, some scientists speculate that life might be possible. If a rogue planet is large enough, it might retain heat from its formation or from tidal heating if it has a large moon. There could be liquid water beneath thick ice shells, similar to what we think exists on some of Jupiter's and Saturn's moons. We've detected a few rogue planets, though they're incredibly hard to find. They don't shine with their own light like stars, and they're not silhouetted against stars like planets we normally detect. We can only find them when they pass in front of more distant stars, briefly magnifying the star's light through gravitational lensing, or when we detect the faint infrared heat they emit. Every few years, astronomers announce the discovery of another rogue planet, and each time, our estimates of how many might exist keep growing. The thought is both lonely and profound. Billions of worlds drifting through the darkness between stars, worlds that may have once known the warmth of a sun, now exiled to wander forever through the cold emptiness of space. Some might still have atmospheres, weather, even oceans beneath ice. But no one will ever see a sunrise on these worlds again. They are the lost children of the galaxy, orphaned worlds floating in an endless night, and we're only beginning to realize how common they might be. For a few seconds, somewhere in the universe, something releases more energy than our sun will produce in its entire 10 billion year lifetime. These are gamma-ray bursts, the brightest electromagnetic events known to occur in the cosmos. They appear without warning from random directions in space, shine with unimaginable intensity, and then fade away, often never to repeat, and despite decades of study, we still don't fully understand what causes them. Gamma-ray bursts were discovered by accident in the 1960s. American military satellites designed to detect nuclear weapons tests picked up mysterious flashes of gamma rays coming from space. The military kept this discovery secret for years, fearing it might reveal the capabilities of their surveillance systems. When the data was finally declassified in 1973, it sparked a scientific mystery that continues today. We now know there are two types of gamma ray bursts. Short-duration bursts last less than 2 seconds and are thought to come from colliding neutron stars. When two of these incredibly dense stellar remnants spiral into each other, they create a kilonova, an explosion that can briefly outshine an entire galaxy. The collision produces a massive burst of gamma rays, along with gravitational waves, ripples in space-time itself. We actually observed this happening in 2017, an event that confirmed many theories about short gamma ray bursts. But long-duration bursts, lasting from a few seconds to several minutes, are more mysterious. The leading explanation is something called the collapsar model. When a massive star runs out of fuel and collapses, it doesn't always become a supernova. Sometimes, under specific conditions, the core collapses directly into a black hole. As matter spirals into the newly formed black hole, it heats up and creates powerful jets of particles and radiation shooting out along the star's rotation axis at nearly the speed of light. If one of these jets points toward Earth, we see a gamma-ray burst. But this explanation has problems. The jets must be incredibly focused, like cosmic laser beams, to produce the energies we observe. The physics of how these jets form and stay collimated is still not fully understood. And there are variations in gamma-ray bursts, different brightness patterns and durations, that don't quite fit the standard models. Some bursts are followed by X-ray afterglows that fade and then suddenly brighten again, behavior that's difficult to explain. Others show no afterglow at all. What makes gamma-ray bursts truly terrifying is their power. If a gamma-ray burst occurred within a few thousand light-years of Earth, and one of its jets pointed at us, the radiation could strip away our ozone layer, exposing the surface to deadly solar ultraviolet radiation. Some scientists have speculated that mass extinctions in Earth's past might have been caused by nearby gamma-ray bursts. Fortunately, they're rare in our galaxy. We might only see one every few 100,000 years. But somewhere in the universe, right now, a star is collapsing or neutron stars are colliding, creating a flash of gamma rays that will travel through space for billions of years, a brief scream of energy from a moment of cosmic violence. From space, particles rain down on Earth constantly. Most are protons, the nuclei of hydrogen atoms, accelerated to tremendous speeds by processes throughout the universe. We call them cosmic rays, though they're particles, not rays. They bombard our atmosphere continuously, creating showers of secondary particles that cascade down to the surface. Most cosmic rays have relatively modest energies, but some are accelerated to energies that seem impossible. In 1991, a detector in Utah registered a cosmic ray particle with an energy of 320 quintillion electron volts. That's 320 followed by 18 zeros. Scientists were so shocked, they called it the "oh my god" particle. To put this in perspective, this single subatomic particle, smaller than an atom, carried the kinetic energy of a baseball traveling at 60 miles per hour. One particle, one proton. With the energy of a thrown baseball, it's almost incomprehensible. The problem is that such particles shouldn't exist. There's a theoretical limit called the GZ-Doc cutoff, named after physicists Greisen, Zastpin, and Kuzmin. When ultra-high energy cosmic rays travel through space, they interact with the cosmic microwave background radiation that fills the universe. These interactions sap energy from the particles. Any cosmic ray traveling more than about 160 million light-years should lose enough energy to fall below certain thresholds. Yet we detect particles with energies above this limit, suggesting they either came from closer sources or somehow bypassed this energy loss. Where do these ultra-high energy cosmic rays come from? What can accelerate particles to such extreme speeds? The most powerful particle accelerators humans have built can't come close to these energies. Even supernovas, the most violent explosions of normal stars, can't explain the highest energy cosmic rays. Scientists have proposed various sources, Maybe they come from the jets of active galactic nuclei, supermassive black holes actively feeding on matter and spewing out jets of particles at relativistic speeds. Maybe they're accelerated in the magnetic fields around pulsars or magnetars. Maybe they come from colliding galaxies or from some exotic process we haven't discovered yet. Another mystery is that these ultra-high energy particles seem to come from specific directions in the sky, not randomly from all directions as you'd expect. Some studies suggest they're clustered, pointing back towards certain regions of space. If we could identify their sources, we might understand what's creating them. But cosmic rays are charged particles, which means they're deflected by magnetic fields as they travel through space. By the time they reach Earth, their trajectories have been scrambled. We can't simply trace them back to their sources like we can with light. Each ultra-high energy cosmic ray is a messenger carrying energy from some catastrophic event, but the message is garbled by its journey through the cosmos. Here's something that's bothered physicists for decades. The surface of the Sun has a temperature of about 5,500 degrees Celsius. That's hot enough to melt any substance we know. But the Sun's atmosphere, called the corona, is much hotter. Parts of it reach temperatures over 1 million degrees Celsius. That's more than 180 times hotter than the surface below it. This is like water being cooler than the steam rising from it. It violates our basic intuition about how heat works. Heat naturally flows from hot to cold. A cooler object touching a hotter object will warm up, but a hotter object doesn't spontaneously become even hotter while in contact with something cooler. Yet that's essentially what the Sun's corona does. Something is pumping enormous amounts of energy into the corona, heating it to millions of degrees while the surface below remains relatively cool. This is called the coronal heating problem, and despite decades of research, we don't have a complete answer. Scientists have proposed many mechanisms. One idea involves magnetic fields. The Sun's surface is covered with powerful magnetic fields that twist and tangle as the Sun rotates. These fields extend up into the corona. When magnetic field lines reconnect, suddenly snapping into new configurations, they release energy that could heat the corona. This is similar to what causes solar flares, sudden explosions on the Sun's surface. Maybe countless small reconnection events are constantly heating the corona. Another possibility involves waves. Various types of waves can travel along magnetic field lines from the Sun's surface into the corona. As these waves propagate upward, they can deposit their energy into the thin coronal gas, heating it. Scientists have observed these waves using space telescopes, and they do carry enough energy to heat the corona. But exactly how the waves transfer their energy to the gas remains unclear. The challenge is that the corona is incredibly thin and tenuous. Even though it's millions of degrees hot, there's so little gas that an astronaut passing through it wouldn't feel much heat. This thinness makes it difficult to study. We can observe the corona during solar eclipses or with special telescopes that block out the Sun's bright disk, but getting detailed measurements of temperature, density, and motion in the corona is challenging. Recent space missions like NASA's Parker Solar Probe, which flies closer to the Sun than any previous spacecraft, are gathering new data that might finally solve this mystery. But for now, every time you look at the Sun, remember that its atmosphere is somehow hundreds of times hotter than its surface, heated by processes we still don't fully understand. Neutron stars are already extreme. When a massive star explodes as a supernova, Its core can collapse into a ball just 20 kilometers across but containing more mass than the Sun. The matter is compressed so densely that protons and electrons merge into neutrons. A teaspoon of neutron star material would weigh about 1 billion tons. But some neutron stars are even more extreme. They're called magnetas, and they have the strongest magnetic fields in the universe. A magneta's magnetic field is about 1 quadrillion times stronger than Earth's. That's 1,000 trillion times stronger. At a distance of just 1,000 kilometers from a magneta, the magnetic field would be strong enough to distort the atoms in your body. The electromagnetic forces would overwhelm the electrical forces holding your molecules together. You wouldn't just die. You would cease to be matter as we understand it. Even from halfway to the moon, a magneta's magnetic field would erase the data on every credit card on Earth. These fields are so powerful they affect space itself. Normally, light travels in straight lines through empty space, but near a magneta, the magnetic field is strong enough to affect photons, causing light to behave strangely. The vacuum of space around a magneta becomes birefringent, meaning it has different refractive properties in different directions, like certain crystals. The fabric of empty space is warped by magnetism. How magnetas get such powerful fields remains somewhat mysterious. The leading theory is that they form from stars rotating extremely rapidly when they collapse. The rotation, combined with the churning motions in the collapsing matter, acts like a dynamo, generating powerful magnetic fields. But the details of this process, the exact conditions needed to create a magneta instead of a normal neutron star, are still being researched. Magnetas occasionally have starquakes. The crust of the neutron star shifts suddenly, like an earthquake but far more violent. These quakes can crack the crust and cause the magnetic field to reconfigure rapidly. When this happens, the magneta releases a tremendous burst of energy. In December 2004, a magneta called SGR 1806, located about 50,000 light-years from Earth, had a giant flare. For 1/10 of a second, it released more energy than the Sun produces in 100,000 years. The burst of gamma rays and X-rays hit Earth's upper atmosphere, ionizing it and affecting radio communications. This from an event 50,000 light-years away. If it had been just 10 light-years away, it could have caused mass extinctions. We don't fully understand how magnetas maintain their fields. Normal magnetic fields decay over time, especially at the high temperatures of neutron stars. Yet magnetas have fields that seem to be sustained for thousands of years. Something about their internal structure or rotation must be maintaining the field, but the physics involved operates at extremes we cannot replicate in laboratories. Magnetas are cosmic laboratories where nature performs experiments we can only dream of, pushing magnetic fields to limits that tear at the structure of space itself. In 2014, astronomers detected something puzzling in X-ray observations of galaxy clusters. A faint emission line appeared at an energy of 3.5 kiloelectron volts, a specific color of X-ray light that didn't correspond to any known atomic transition. This signal appeared in multiple galaxy clusters and even in observations of our own galaxy's center. At first, it seemed like it might be instrumental noise or some systematic error, but the signal kept appearing in independent observations from different telescopes. This mysterious X-ray line sparked excitement because it appeared at an energy consistent with one theoretical prediction for dark matter decay. Some models of dark matter predict that dark matter particles might very slowly decay into photons. If dark matter particles with a mass of about 7 keV decayed, they would produce X-rays at exactly 3.5 keV. Galaxy clusters contain enormous amounts of dark matter, so if this signal was real, it could be the first direct detection of dark matter particles. Scientists scrambled to confirm or refute the finding. Some observations supported it, others didn't see the signal at all. Some researchers proposed alternative explanations. Maybe it was emission from hot potassium plasma, an unexpected but possible source. Maybe it was an instrumental artifact that happened to appear at the same energy in multiple telescopes. The debate continues, with new observations sometimes strengthening the case for the signal and other times weakening it. Beyond this specific mystery, galaxy clusters emit X-rays that sometimes show unexpected features. Hot gas trapped in the clusters glows in X-rays, and by studying this emission, astronomers can learn about the temperature, density, and composition of the gas. But occasionally, they find emission lines or absorption features that don't quite match expectations. Some of these anomalies might be rare atomic transitions we don't usually observe. Others might be evidence of exotic physics or unknown particles. The universe at X-ray wavelengths looks very different from the visible light universe. X-rays are produced by extremely hot gas, by matter falling into black holes, by supernova remnants, and by other violent processes. Every time we build more sensitive X-ray telescopes, we discover new phenomena we didn't expect. The mysterious X-ray signals remind us that even our best understanding of physics might be incomplete, that there could be particles or processes we haven't discovered yet, waiting to be revealed in the high-energy light from distant galaxies. In old star clusters, there's a puzzle. These clusters formed billions of years ago, and all their stars should have aged together, like classmates growing old. The most massive stars should have long since burned out and died, leaving behind only smaller, dimmer, older stars. Yet in many old clusters, astronomers find blue stragglers. These are bright, blue, young-looking stars in clusters full of old red stars. They're like finding teenagers at a retirement home. They shouldn't be there. Blue stragglers are too young for their environment. The clusters are billions of years old, but these stars appear to be only a few 100 million years old. They're more massive than the other stars in the cluster, which means they should have died long ago. Massive stars burn their fuel quickly, living fast and dying young. So how are these stars still shining? The answer seems to be that they're not actually young. They're old stars that have been rejuvenated somehow, given new fuel to burn. The leading explanation involves stellar collisions or mergers. In dense star clusters, stars are packed closely together over billions of years. Some stars will collide or pass close enough to gravitationally interact. When two stars merge, they combine their mass and their remaining hydrogen fuel. The merged star becomes hotter, bluer, and more massive than either original star. It looks young, even though its components were old. It's like mixing two dying embers together and creating a brighter fire. Another possibility involves binary star systems. If two stars orbit each other closely enough, one star can pull matter from its companion. This mass transfer can rejuvenate the star receiving the matter, making it appear younger and bluer. Over time, it might even consume its entire companion, becoming a single blue straggler. Computer simulations and observations support both mechanisms. In some clusters, blue stragglers are found near the center, where collisions are more likely. In others, they show evidence of having binary companions. But the details are still being worked out. How often do these collisions happen? How do the properties of the original stars affect the blue straggler that forms? Can we tell by looking at a blue straggler whether it formed from a collision or from mass transfer? These questions matter because blue stragglers tell us about the dynamical history of star clusters, about how stars interact over billions of years in these dense environments. Every blue straggler is a survivor, a phoenix risen from the ashes of older stars, shining bright in a cluster that should have long since faded to red and orange. When scientists add up all the sources of light in the universe, something doesn't match. The amount of optical and ultraviolet light filling space, called the cosmic optical background, appears to be higher than it should be based on all the known sources. It's as if there's a faint glow permeating the universe that we can't account for. Galaxies produce light. Stars produce light. Active black holes produce light. When we add up all these known sources and calculate how much light should be traveling through space, we get a number that's too small. This excess light was first clearly measured by NASA's New Horizons spacecraft, the probe that flew by Pluto and is now traveling through the outer solar system. From its distant vantage point, far from the sun and most of the zodiacal dust in our solar system, New Horizons can measure the darkness of space more accurately than any Earth-based observatory. And space isn't quite as dark as it should be. There's extra light, a diffuse cosmic glow coming from all directions. Where is this extra light coming from? One possibility is that there are more faint, distant galaxies than we've detected. Our telescopes have limits. We can see bright galaxies at great distances, but very faint, diffuse galaxies might escape detection. If space is filled with countless small, dim galaxies that we're missing, they could contribute enough light to explain the excess. Recent deep observations with powerful telescopes like Hubble and James Webb have found many faint galaxies, but it's not clear if there are enough to fully explain the cosmic optical background. Another intriguing possibility is that some of the light comes from stars between galaxies. Not every star lives in a galaxy. Some float in the vast spaces between galaxies, either ejected from their home galaxies by gravitational interactions or formed in intergalactic space during galaxy collisions. These intergalactic stars would be nearly impossible to detect individually because they're so far away and so isolated. But collectively, they might produce a faint glow that contributes to the cosmic optical background. More exotic explanations propose that the excess light could come from decaying dark matter particles. If dark matter particles occasionally decay into photons, the cumulative effect over cosmic history might produce a faint background glow. Or perhaps the light comes from the very first stars that formed in the universe, massive objects that burned bright and brief billions of years ago. Their light would have redshifted, stretched by the expansion of the universe, until it appears in optical wavelengths today. The cosmic optical background is a subtle mystery, easy to overlook. But it reminds us that even something as basic as accounting for all the light in the universe remains challenging. There's a faint glow out there, filling the darkness between galaxies, and we're not entirely sure where it's coming from. Neutrinos are ghost particles. They have almost no mass, carry no electric charge, and barely interact with matter. Trillions of them are passing through your body right now, streaming from the sun and cosmic rays, going through the Earth as if it wasn't there. To a neutrino, matter is almost transparent. They can pass through light years of solid lead without being stopped. This makes them incredibly difficult to detect. To catch neutrinos, scientists build massive detectors deep underground or in clear ice, waiting for the rare moment when a neutrino happens to interact with an atom. Most neutrinos we detect have low energies. They come from the sun, from supernovas, from nuclear reactors, from cosmic rays hitting Earth's atmosphere. But occasionally, detectors pick up a high-energy neutrino. And sometimes, very rarely, they detect a neutrino with truly extreme energy, billions of times more energetic than typical cosmic neutrinos. These high-energy neutrinos are messengers from the most violent events in the universe, and often we have no idea what created them. In 2013, the Ice Cube detector in Antarctica detected two high-energy neutrinos that researchers named Bert and Ernie after the Sesame Street characters. These neutrinos had energies over 1 million times higher than neutrinos from the sun. They must have come from cosmic sources, likely from outside our galaxy. But when scientists traced back their trajectories, the directions didn't point to any obvious sources. No active galaxies, no supernova remnants, no gamma-ray bursts. Just empty regions of sky. Since then, IceCube has detected more high-energy neutrinos. In 2017, one neutrino was traced back to a blazar, an active galaxy with a jet pointed toward Earth. This was exciting because it confirmed that blazars can produce high-energy neutrinos. But blazars can't explain all the high-energy neutrinos we detect. Some come from directions where there are no known blazars or other obvious sources. Something out there is accelerating particles to tremendous energies and producing these neutrinos, and we often can't identify what it is. Neutrinos are valuable because, unlike light or charged particles, they travel in straight lines from their source to us. Light can be absorbed by dust. Charged particles are deflected by magnetic fields. But neutrinos ignore these obstacles. If we can detect a high-energy neutrino and trace it back to its source, we can learn about processes happening in environments that are completely opaque to light. We can see into the hearts of collapsing stars, into the jets of black holes, into regions where matter is being accelerated to the highest energies in the universe. But detecting neutrinos is so difficult and rare that we've only begun to build up a catalogue of high-energy neutrino events. Each one is precious, a data point revealing something about the extreme universe, and many of them remain unexplained, pointing to unknown sources, carrying energy from cosmic accelerators we haven't identified yet. The neutrinos are trying to tell us something about the universe's most violent phenomena, but we're only beginning to learn their language. When stars explode as supernovas, they should create zombie stars, dead stellar remnants that somehow survive their own destruction. These objects shouldn't exist according to our simplest models, yet we found them. When certain massive stars reach the end of their lives, they undergo what's called pair instability supernovas. The core becomes so hot that gamma-ray photons spontaneously create pairs of particles and antiparticles. This saps energy from the core, causing it to collapse, which triggers a runaway thermonuclear explosion so powerful it should completely destroy the star. Nothing should remain. No neutron star, no black hole, just an expanding cloud of debris. But in 2014, astronomers watched a supernova called IPTF14H that kept exploding. It brightened, faded, then brightened again, and again. Over 3 years, it erupted multiple times, ejecting material and shining brilliantly, behavior that's impossible for a normal supernova. Models of stellar explosions couldn't explain it. Some researchers proposed it might be a pulsational pair instability supernova, where the star undergoes multiple pulses of instability, ejecting its outer layers in stages over years or decades, before finally destroying itself completely. Other mysterious supernova remnants suggest that some stars survive explosions that should have destroyed them. In a few cases, astronomers have identified stars at the centers of supernova remnants, stars that appear to be the progenitors that somehow survived their own supernovas. These zombie stars challenge our understanding of stellar death. How can a star explode and survive? What mechanisms allow a star to eject large amounts of mass in a supernova-like event without completely destroying itself? The physics involved operates at the limits of what our models can predict in conditions of extreme temperature, density, and nuclear reaction rates. These stellar zombies are rare, which makes them hard to study. Each one is a unique puzzle, a star that defied death, clinging to existence despite undergoing processes that should have annihilated it. They're reminders that the deaths of stars can be even stranger and more varied than we imagined, that the universe finds ways to surprise us even in phenomena we thought we understood. Time only moves in one direction. You remember the past, but not the future. Eggs break, but don't spontaneously reassemble. Stars burn out, but don't unburn. This seems obvious, fundamental to our experience of reality. But here's the mystery. The laws of physics don't care which direction time flows. Almost every equation in physics works exactly the same whether time moves forward or backward. If you filmed subatomic particles interacting and played the video in reverse, the reversed version would still obey the laws of physics. Yet our universe clearly has a preferred direction for time. This is called the arrow of time, and physicists still debate why it exists. The answer seems to lie in something called entropy. Entropy is a measure of disorder, of how spread out and random things are. The second law of thermodynamics says that entropy always increases in closed systems. Things naturally move from ordered states to disordered states. A drop of ink spreads through water. Heat flows from hot to cold. Broken eggs don't reassemble. All these phenomena point in the same direction, toward increasing entropy, and this gives time its arrow. But this raises a deeper question. Why was entropy so low in the early universe? The Big Bang started with matter and energy in an incredibly smooth, uniform, low entropy state. If the universe had started with high entropy, with everything already maximally disordered, there would be no arrow of time. Nothing would change. No stars would form. No life would arise. The fact that we exist, that time flows, that things happen, all depends on the universe starting in a very special, very unlikely low entropy state. Why? What set the initial conditions? Some physicists argue that the arrow of time is an illusion, that at the deepest level, time has no direction and our perception of flowing time emerges from statistical properties of complex systems. Others suggest that the low entropy beginning is connected to cosmic inflation, the rapid expansion of space in the first fraction of a second after the Big Bang. Inflation might have naturally created a universe with low entropy, smoothing out irregularities and setting the stage for the arrow of time we experience. There's also a connection to consciousness and memory. We remember the past because our brains create physical records, memories encoded in neural structures. These memories are forms of increased entropy. We can't remember the future because we can't create records of things that haven't happened yet. Some philosophers and physicists have proposed that consciousness itself is intimately connected to the arrow of time, that our subjective experience of time flowing is linked to the thermodynamic arrow. The mystery deepens when you consider that time might eventually lose its arrow in the distant future, when all stars have burned out, when all black holes have evaporated, when the universe reaches maximum entropy, nothing will change anymore. The universe will reach a state called heat death, where everything is the same temperature, the same density, the same level of disorder. In such a universe, there would be no meaningful distinction between past and future. Time would still exist in some abstract sense, but nothing would happen. The arrow of time would vanish. We live in a special epoch, billions of years after the low entropy beginning, but trillions of years before the high entropy end, when time has meaning and direction. But we still don't fully understand why. Quantum entanglement is often called spooky action at a distance. When two particles become entangled, they become connected in a way that transcends normal ideas of space and separation. If you measure one particle and find it has a certain property, the other particle instantly has a related property, no matter how far apart they are. This isn't just correlation. It's as if measuring one particle affects the other faster than light could travel between them. Einstein found this troubling because it seemed to violate the principle that nothing can travel faster than light. Decades of experiments have confirmed that entanglement is real. It's not a measurement error or a misunderstanding. Particles really do become connected in this strange way. But here's what makes it mysterious at cosmic scales. Entanglement seems to work regardless of distance. Two particles could be separated by millions of light years, and measuring one would still instantly affect the other. The connection doesn't weaken with distance. It doesn't care about the space between the particles. Scientists have performed entanglement experiments over larger and larger distances. Satellites have entangled photons across thousands of kilometers. Researchers have proposed experiments to test entanglement between Earth and the Moon, or even between different planets. So far, no experiment has found any distance limit to entanglement. This raises profound questions. How does the universe maintain these connections? Is there some underlying structure to space that allows entanglement to work? Are entangled particles connected through dimensions we can't perceive? Some physicists have speculated that entanglement might be related to the structure of space-time itself. In certain quantum theories of gravity, space-time emerges from entanglement. The geometry of space, the distances between objects, might arise from patterns of quantum entanglement at the deepest level. If this is true, then entanglement isn't happening in space. Space is happening because of entanglement. This is a radical idea that turns our usual picture of reality inside out. There's also the question of what happens to entanglement as the universe expands. Space itself is stretching, carrying galaxies apart. Does this expansion affect entangled particles? if two particles were entangled billions of years ago and have since been carried to opposite sides of the observable universe by cosmic expansion, are they still entangled? Does the expansion of space break the entanglement? Or does the connection persist across expanding space? These questions touch on the intersection of quantum mechanics and cosmology, two theories that don't yet fit together seamlessly. Entanglement also raises puzzles about information and causality. You can't use entanglement to send information faster than light, which preserves causality and prevents paradoxes. But the fact that measurement outcomes are correlated instantaneously across cosmic distances suggests that, in some sense, information about the quantum state is non-local, spread out across space in ways we don't fully understand. Entanglement challenges our intuitive notions of separateness and locality. The universe, at the quantum level, is deeply interconnected in ways that transcend distance and space. Here's one of the most embarrassing problems in theoretical physics. When scientists calculate how much energy should exist in empty space based on quantum theory, they get an answer. When they measure how much energy actually exists in empty space based on cosmological observations, they get a different answer. The two numbers disagree by about 120 orders of magnitude. That's not a typo. The theoretical prediction is 10 to the 120th power times larger than observations. It's the worst prediction in the history of science. This is called the cosmological constant problem, and it's closely related to the mystery of dark energy. According to quantum field theory, even empty space should be filled with virtual particles popping in and out of existence. These quantum fluctuations should contribute energy to the vacuum of space. When physicists calculate this vacuum energy, the number they get is enormous. So enormous that if it were real, the universe would have expanded so violently that atoms couldn't form. Galaxies, stars, planets, life, none of it could exist. But clearly, we do exist. The actual vacuum energy, measured by observing how the universe expands, is tiny. It's not zero, which is why we have dark energy causing the accelerated expansion of the universe. But it's vastly smaller than theory predicts. Why? What cancels out or suppresses the quantum vacuum energy to such an incredible degree? And why doesn't it cancel completely? Why is there any vacuum energy at all? Some physicists have invoked the anthropic principle. Maybe the vacuum energy varies across different regions of a vast multiverse. In regions where it's too large, the universe expands too fast for structures to form. In regions where it's too negative, the universe collapses immediately. Only in regions where the vacuum energy happens to be small and positive, like ours, can galaxies and life emerge. We find ourselves in such a region not because the laws of physics prefer it, but because only such regions can be observed by beings like us. This explanation is philosophically troubling to many scientists because it seems to give up on finding a deeper reason. Others hope for new physics. Maybe there's a symmetry or mechanism we haven't discovered that explains why the vacuum energy is so small. Supersymmetry, a proposed extension of the standard model of particle physics, could potentially address the problem, but experiments haven't found evidence for supersymmetry yet. Alternative theories of gravity might change the calculation. Or maybe our understanding of quantum field theory in curved spacetime is incomplete, and the proper calculation would yield a different result. The cosmological constant problem is a reminder that even our most successful theories, quantum mechanics and general relativity, don't fit together perfectly. When we try to combine them, we get nonsensical predictions. A complete theory of quantum gravity might resolve the problem, but we don't have such a theory yet. For now, the cosmological constant problem stands as one of the deepest unsolved mysteries in fundamental physics, a glaring discrepancy between theory and observation that humbles our understanding. Black holes create a paradox that's troubled physicists for decades. According to general relativity, anything that falls into a black hole is lost forever, crushed into the singularity at the center. But according to quantum mechanics, information cannot be destroyed. Every quantum state, every configuration of particles and fields, must be preserved in some form. These two principles seem to contradict each other at black holes. When matter falls into a black hole, what happens to the quantum information it carried? This is the black hole information paradox. Stephen Hawking made the problem worse in the 1970s when he showed that black holes aren't completely black. They emit radiation due to quantum effects near the event horizon. This Hawking radiation causes black holes to slowly evaporate over immense timescales. A black hole with the mass of the Sun would take 10 to the 67th power years to evaporate, far longer than the current age of the universe. But given enough time, even supermassive black holes will eventually disappear in a final burst of radiation. Here's the paradox. Hawking radiation appears to be completely random, carrying no information about what fell into the black hole. If a black hole evaporates completely and all that's left is random radiation, the information about the matter that formed the black hole and everything that fell into it seems to be lost. This violates quantum mechanics. It's as if you burned a book and somehow the information in the book disappeared from the universe entirely, not just scattered as ashes, but truly destroyed. Quantum theory says this shouldn't be possible. Physicists have proposed many solutions. Maybe the information isn't lost. Maybe it's encoded in subtle correlations in the Hawking radiation in ways we haven't figured out how to calculate. Maybe the information is stored on the event horizon of the black hole in some form. This idea led to the holographic principle, which suggests that all the information in a volume of space can be encoded on its boundary, like a hologram. Maybe black holes don't completely evaporate. Maybe tiny remnants remain, containing all the information. Or maybe our understanding of space-time breaks down at black holes, and the paradox reveals the need for a theory of quantum gravity. Recent work suggests that information might escape from black holes through quantum entanglement between the Hawking radiation and the interior of the black hole. As particles are emitted, they become entangled with particles inside, gradually transferring information outward. After the black hole has evaporated past a certain point, all the information that fell in would be encoded in the radiation that escaped. This resolves the paradox, but requires complex quantum computations to verify. The information paradox matters because it probes the deepest foundations of physics. It asks what happens when gravity, space-time, and quantum mechanics collide. The answer will likely require new physics, a unified theory that encompasses both quantum mechanics and general relativity. Black holes are laboratories where nature conducts experiments in extreme physics, and the information paradox is one of the most important puzzles they present. The universe is flat. Not flat like a pancake, but geometrically flat in a precise mathematical sense. If you draw a triangle with light beams in space, the angles add up to exactly 180 degrees. If the universe were curved like the surface of a sphere, the angles would add up to more than 180 degrees. If it were curved like a saddle, they'd add up to less. Measurements show that the universe is flat to incredible precision, within less than 1% of perfectly flat. This is the flatness problem, and it's more mysterious than it might sound. In the early universe, right after the Big Bang, the geometry of space could have been anything. It could have been highly curved in one direction or another, but curvature evolves over time. An almost flat universe stays almost flat. A curved universe becomes more curved. For the universe to be as flat as we observe today, it must have been extraordinarily flat in the beginning, fine-tuned to 1 part in 10 to the 60th power or better. That's like balancing a pencil on its point and finding it still balanced billions of years later. Why was the early universe so flat? This seems like an incredible coincidence unless there's a reason. The leading explanation is cosmic inflation. In the first tiny fraction of a second after the Big Bang, space expanded exponentially, growing by a factor of at least 10 to the 26th power in less than 10 to the minus 32 seconds. This violent expansion would have stretched out any curvature, flattening the universe like inflating a balloon flattens its surface. After inflation, the universe would naturally be extremely flat, solving the flatness problem. But inflation itself raises questions. What caused it? What kind of field or energy drove this rapid expansion? The leading candidate is something called the inflaton field, a hypothetical energy field that filled the early universe. But we don't know what the inflaton was made of or how it worked. We've never detected it directly. Inflation is supported by observations of the cosmic microwave background, which show patterns consistent with inflation's predictions, but the details remain uncertain. There's also the question of why inflation stopped. If space was expanding exponentially, what made it suddenly slow down to the more gradual expansion we see today? The standard answer is that the inflaton field decayed, converting its energy into particles and radiation, reheating the universe and ending the inflationary period. But the mechanism for this decay, the precise physics involved, is still being worked out. The flatness of the universe is one of those facts that seems simple, but reveals deep mysteries when you examine it closely. Why is space geometrically flat? Why does the universe have the precise properties needed for inflation to work? These questions connect to the fundamental structure of space and time themselves. Related to the flatness problem is the horizon problem. The cosmic microwave background, the light from the early universe, looks almost exactly the same temperature in all directions. The temperature varies by only about 1 part in 100,000 from place to place across the sky. This uniformity is puzzling because regions on opposite sides of the sky were never in contact with each other in the early universe. They were too far apart for light to travel between them. So how did they end up at the same temperature? If two regions never communicated, never exchanged energy, how did they reach thermal equilibrium? It's like finding that two isolated islands have exactly the same average temperature even though no heat or information has ever passed between them. Without some mechanism to smooth out temperature differences, we'd expect the cosmic microwave background to have large temperature variations from one region to another. But it doesn't. Again, inflation provides an answer. Before inflation, the entire observable universe was compressed into a tiny region, small enough that all parts were in thermal contact. Everything reached the same temperature. Then inflation stretched this tiny uniform region into the vast universe we see today. All parts of the observable universe were once close enough to interact, which explains why they have the same temperature now, even though they appear to be separated by distances too large for light to cross since the Big Bang. But without inflation, the horizon problem remains unsolved. And even with inflation, we need to explain what caused it and how it worked. The horizon problem is a clue, a piece of evidence pointing towards some dramatic event in the first instance of cosmic history that smoothed out the universe and set the stage for everything that followed. Near massive objects, time flows differently. Einstein's general relativity predicts this, and it's been confirmed by countless experiments. Clocks run slower in strong gravitational fields. An astronaut orbiting near a black hole would age slower than someone far from the black hole. This is called gravitational time dilation, and it's a well-established feature of reality. But there are mysteries and unexplained variations that still puzzle scientists. For example, precise measurements of time dilation near Earth sometimes show tiny anomalies that don't quite match predictions. These discrepancies are small, often within measurement error, but they persist. Some researchers have wondered whether these anomalies hint at new physics, perhaps related to dark matter or modifications to gravity at small scales. Others think they're just measurement challenges, the difficulty of accounting for every factor that affects ultra-precise atomic clocks. There's also the mystery of what happens to time inside black holes. General relativity predicts that time behaves strangely near singularities. Some calculations suggest that time might flow in different directions, or even become space like inside the event horizon. The concept of before and after might break down entirely. But we can't observe the inside of black holes, so these remain theoretical speculations. Time dilation also plays a role in cosmology. Light from distant galaxies is stretched by the expansion of space, causing red shift. But this redshift also affects how we perceive time in those galaxies. Events that took days in a distant galaxy appear to take weeks or months from our perspective, because the expansion of space stretches time itself. Supernovas in very distant galaxies explode and fade in slow motion from our point of view. This is time dilation on cosmic scales, a consequence of living in an expanding universe. Some physicists have speculated about even stranger time effects. Could there be regions of space where time flows backward? Could wormholes, if they exist, create closed time like curves, paths through space-time that loop back to the past? General relativity allows such solutions mathematically, but whether they exist in reality and what would prevent paradoxes is unknown. Time remains one of the most mysterious aspects of the universe, familiar in our everyday experience, yet deeply strange when examined through the lens of modern physics. Wormholes are shortcuts through space-time, tunnels connecting distant regions of the universe or even different universes. They're allowed by the equations of general relativity, but whether they actually exist is unknown. The mathematics says they're possible, but physics imposes severe restrictions. For a wormhole to be traversable, to allow something to pass through without being crushed, it would need to be held open by exotic matter with negative energy density. We've never found such matter in nature. Quantum field theory suggests that negative energy might exist in tiny amounts under special circumstances, a phenomenon called the Casimir effect. Two metal plates placed very close together in a vacuum can have less energy between them than in the vacuum outside, creating a kind of negative energy pressure. But the amounts are minuscule, nowhere near enough to stabilize a wormhole large enough for even a particle to traverse, let alone a spaceship. Some physicists have explored whether advanced civilizations could create and maintain wormholes using technologies far beyond our current capabilities. But these remain speculations. Even if wormholes exist naturally, they might be unstable. Any disturbance, even a single photon passing through, might cause them to collapse. Or they might connect to regions of space-time so violent, so extreme, that nothing could survive the journey. The equations allow wormholes, but nature might have other ideas. There's also the question of whether wormholes could lead to time travel paradoxes. If a wormhole connects 2 points in space and time, you might enter one end and emerge from the other before you left, creating a path into the past. This raises all the classic time travel paradoxes. Could you prevent your own journey? General relativity allows these closed time-like curves mathematically, but most physicists suspect that quantum effects or unknown laws of physics prevent them from forming in reality. Wormholes represent one of the most speculative areas of cosmology. They're mathematically beautiful, tantalizing shortcuts that would make interstellar or even intergalactic travel feasible. But we have no evidence they exist, and many reasons to doubt they could be stabilized or used. Still, they remain a possibility, a feature of space-time allowed by our best theory of gravity. If we ever discover a wormhole, or figure out how to create one, it would revolutionize our understanding of space, time, and what's possible in the universe. Quantum mechanics describes the microscopic world with incredible precision. It predicts the behavior of atoms, photons, and particles with remarkable accuracy. But quantum mechanics is also deeply strange. It says that particles exist in superpositions, being in multiple states at once until measured. It says that the act of measurement causes the quantum state to collapse, randomly selecting one outcome from many possibilities. This is the measurement problem, and at cosmic scales, it becomes even more mysterious. When does a quantum superposition collapse? If an electron can be in 2 places at once until measured, what counts as a measurement? Does it require a conscious observer? Does it happen automatically when the quantum system interacts with a large classical system? Different interpretations of quantum mechanics give different answers, and none are fully satisfying. The problem becomes acute when we think about the entire universe. If the universe itself is a quantum system, as many theories suggest, then it should be in a superposition of all possible states. But we observe a definite state. Why? This is related to the question of how classical reality emerges from quantum mechanics. Why do large objects like planets and stars behave classically, following definite trajectories, while microscopic particles behave quantum mechanically? The answer involves something called decoherence. Quantum systems lose their superposition when they interact with their environment, becoming entangled with countless particles around them. This causes quantum behavior to wash out at large scales, giving rise to the classical world we experience. But decoherence doesn't fully solve the measurement problem. It explains why we don't see large objects in superposition, but it doesn't explain why measurement outcomes are definite rather than remaining in superposition at a fundamental level. Some interpretations, like the many worlds interpretation, propose that all measurement outcomes actually occur, each in a separate branch of reality. Every quantum measurement causes the universe to split into multiple copies, one for each possible outcome. We experience only one outcome because we live in one branch, but all branches are equally real. Other interpretations suggest that quantum mechanics isn't the final theory, that there's a deeper level of reality where things are deterministic, and the randomness we observe is due to hidden variables we can't access. But experiments testing hidden variable theories have generally supported standard quantum mechanics. The measurement problem remains unresolved, a philosophical and scientific puzzle at the heart of our best theory of matter and energy. At cosmic scales, the measurement problem raises even stranger questions. When we observe the cosmic microwave background, we're measuring quantum fluctuations from the early universe that have been stretched to cosmic proportions by inflation. These fluctuations were once subatomic quantum uncertainties. Now, their temperature variations spread across billions of light years. How and when did these quantum fluctuations become classical? Did they collapse when inflation ended? Or do they remain in superposition in some interpretations? The line between quantum and classical at cosmic scales is blurry, and we don't fully understand where or how that line is drawn. We've journeyed through 50 mysteries, from signals that vanished into silence to particles carrying impossible energy, from stars that shouldn't exist to voids that stretch across the cosmos, from the arrow of time to the edge of everything. Each mystery is a question the universe has posed to us, a puzzle waiting to be solved. Some of these mysteries might find answers in our lifetimes. New telescopes, new experiments, new theories might explain what once seemed